Hello, my friends. This is Dr. Mohamed Nezami again with another presentation on the design and analysis and modeling of 5G RF transceivers. Please check my playlist for this series on 5G small cell transceiver design. We're doing RF hardware designs. Today, this is going to be the last part. Since last part, I did the design and system analysis of a sub 6 gigahertz 5G small cell transceiver, namely 1 watt transceiver. We showed the modeling and all that. And in fact, let me see if I can in here. These are the presentations that I've done so far on the 5G. So we got 1, 2, 3, 4, 5, and today's part is 6. So this is part 6 today. Last time we did this part here where we showed the modeling of a sub 6 5G 3.5, 3.6 gigahertz transceiver design, 1 watt. And we showed how this design is done. I'm going to briefly just repeat on that. You can also check my the rest of my videos in here for your interest. And please, if you could do me a favor, just go ahead and subscribe to the channel. I would appreciate it. That way you get, every time I uploaded a video, you get that video. And also, that also gives you some support. Now you can go into any of these videos and view the details. But for right now, let's go ahead and start today's session. And today, we're going to finish the part where we are going to look at the design and analysis of a today we're going to cover the 28 gigahertz or the millimeter wave transceiver design, and the difference between, as you know, the sub 6 gigahertz 5G small cell transceivers and millimeter waves is that they both have MIMOs, but the sub 6G does not have beamforming. Now the millimeter wave is the one where it has a has beamforming, beam steering capabilities. So I'm going to grab off the shelf one of those chip ICs from the manufacturers. There's various numbers of manufacturers who design chipsets for the 28 gigahertz or for the millimeter band from 24 gig to 50 gig for the 5G. So I'm going to pick one of those and illustrate a design and model the system level aspects of the transceiver using the Pathwave SystemVue. Just as a reminder, I'm an RF consultant, independent consultant. I operate out of Jerash, Georgia, and this is my rate right now, running at $20 per hour if you have a design. And I've started on one client already, so I still got a little bit of time to work with others if things don't warm up soon. You can contact me. I produce RF boards really quick, turn in schematics and BCB and bit of material. And I will also travel to your site and help you out with the testing and system integration as well. You can reach me at this email. I have a phone number that I will show at the end of the. So just as a reminder, now the beamforming capabilities of the 5G millimeter wave starts out at this. Or let's just look at the antenna panel array for both the sub 6G and the millimeter wave. For these small cells and even macro cells, the antennas are done as follows. Usually these antennas transmit both polarization, dual polarization. They don't transmit vertical and horizontal like SATCOM transceivers. In here, they somehow suggested that the polarization is slightly rotated by 45 degrees for both the vertical and horizontal. So they have a name for it, which is slanted plus minus 45 degree antenna. So what you see here, the two different colors is basically corresponding to the different polarization. And it's almost like a standard. If you look at the standards, they all talk about 8-element subarray. Okay, so you get 8-element subarray at minus 45 degrees oriented, another one at plus 45 degrees. You put them together, they're orthogonal, so they don't interfere with each other, or to a certain extent. And this is what you end up with. This is the standard subarray cell for most of these 5G transceivers, okay, the antenna panels. Now, this one here, because it's got vertical and horizontal, so this is really 2 transmitters, 2 receivers. And the reason is because we're sharing the antenna for both the receiver and the transmitter. It's a time duplexing system, so therefore, this antenna here is hooked up to 2 transmitters, one for the plus 45 degrees, one for the minus 45 degrees. Now you could either transmit this is for the system designer to decide, or the system deployer. You could decide to transmit the same data on both antennas, in which you would be doing transmit diversity, or you would be transmitting 2 different independent streams of data. So you end up doubling the data rate, okay, doubling the information rate that is going down or going up. Of course, well, this is going down because this is really, we're talking about the cell side. We're not talking about the handset. The handset, if you look at the handset, usually for millimeter, they've got 4 arrays, 2 on each side of the phone, away from the places where you usually hold it with your hand. Usually it's on this side or this side. And you can check those out. So those are mostly 2 transmit, 2 receives, or actually 4, because there's 4 elements in there. Each one is dual polarized. Now, to get more capacity coverage, you could now start cascade putting more and more of these panels. So you, like, if you put another one, that's 4 transmit, 4 receives. Okay. Now you double that, you get 8 transmit, 8 receives, and then you get double that, you end up with a case like this, of course. Now, this is in this case, it's a 64 transmit, 64 receive. That's a little different in here. This is 8 by 8. So there's 64. Each one of these guys is hooked up to a transmitter, okay? Now, I will show in a minute how is that configured. So you can go back to this and start slicing this. You could have it 4 antennas on top and 4 antennas on the bottom. Now you've got subarray of 4 here, subarray of 4. So you end up with 2 transmit here, 2 receives, and 2 transmit, 2 receives. So you can actually convert this vertically also to 8 transmit, 4 transmit, 4 receives. Now, and that is this slide here. So I took this out of the 5G organization. And so in here, what they do is they show you, let's take this Google Earth map of a geographical area where it is basically urban, a dense urban like this, and then urban like this, and then rural areas like this, where it's like a countryside, you know, where scattered houses and facilities. So you could configure this, and so why am I covering this? I'm really doing a hardware design. I'm trying to demonstrate the RF components. I'm going to pick RF components off the shelf from semiconductor manufacturers to build a transceiver for at millimeter waves at 28 gigahertz plus minus 200 megahertz bandwidth. But the reason I'm doing this is because I want to show you why what's coming up ahead. We need to understand the system so that you actually can understand why I'm designing this. For instance, why am I using 2 DACs, 2 ADCs in the digital generation section, okay, and so forth. So you need to see the complexity of this transceiver, because it's in a transceiver that drives an array like this, So it needs to be designed, and we need to understand the antenna usually how it's deployed. So for these different areas in here, you really can't use throughout all of them the same antenna beam forming network, because obviously when you have areas like this where it's rural areas, you can have basically a base station that will shoot the beams to specific areas where there is cover that there's a demand for data. And then so they're sporadically displaced, and so therefore in this case here you would need like a you don't have a lot of capacity demand, you have a lot of coverage because you have a house in here and then 10 miles away all empty until the next house. So you really need a big beam, but not necessarily a lot of transceivers to cover because there is no demand for data rate. And that's basically like a case like this where you have 8 elements by 8 columns, okay? And each one of these is connected to a transmitter. So you've got 8 transmitters, 8 receivers for every polarization. So that's 16. A case like this, of course, that would work very well for the rural areas where you have 1 by 8. So all you need is 1 by 8, and each one of these is you would point to a certain section, or you could displace these beams uniformly in 360 degrees. Now, contrary to that, if you look at the dense areas, you might have a single building that needs dedicated 3 beams in it, cover it, because it's a high rise and it's got a lot of people living in, like shopping malls and so forth. So in a case like this, for instance, you would need 64 transmitters, which is a case like this. That's where we would narrow the beam and just basically, unlike this, we don't use 1 transmitter driving 8 antennas. We use 2 antennas, 2 transmit, 2 receives on each polarization, and then we can have many of these, okay? And that would be 64 of them in this case, okay, to do this. This is an example of a 28, okay? So that's a different situation. So, and for instance, you can also have an area like this where you can have something in between this dimension and this dimension. That would be 4 antenna subarrays to cover, and each one of these is a beam. That would be nice for this, okay, for the suburban or urban areas, okay? Now, so you can see that the basically the radio, as far as the radio transceiver, the number, you need a number of transceivers to drive these. So depending on if it's a case like this, you have 2 transceivers, okay? You have 1 here, 1 here, 1 driving the plus 45, 1 driving the negative 45. In a case like this, you have 4 of them, of course. You have 2 in each column, so that's 4 of them. In a case like this, you have 8 of them, because you have 1, 2, 3, 4, and each 4, they're orthogonal. You have to double that for both polarization. Internally, the antennas basically have some kind of passive network that distributes the signal to them, just like I'm showing here. Okay, so let's just review what we did last time, because what we're going to end up doing is, I suggested this from the beginning. We know that there's a difference in bandwidth between the sub-6 gig and the millimeter wave bands for the 5G small cell transceivers. But what I'm going to do is, I designed last time a sub-6 gigahertz small cell 1 watt transceiver that has a broad bandwidth that you could scale scale the filters down, so you could actually use 400 megahertz bandwidth and then utilize that make the whole transceiver will become, the low power section of it will become an intermediate frequency to the millimeter wave transceiver, to make up a millimeter transceiver. Because from a sub-6 G transceiver, which operates somewhere, say, up to 6 gig, from 2 to 6 gig, what you would need only an up converter and down convert, take it up to the 28 or 24 to 50 gigahertz, somewhere in there. So, and that's the approach I have. So let's just review. Last time what we did, we took a device, which is the 8991 Let's see this one. Okay, it's the 9081, sorry. The 9081, basically it's a transceiver front end. Basically, it's got 4 digital to analog converters running at 16-bit, running at 12 gigasamples per second. And we have 4 A to D's 12 bits running at 4 gigasamples per second. And I showed last time how you can go from here, from bits to antennas, basically, without any frequency conversion. So this would be here, would save as a 4 transmit, 4 receive system. So what we did is we took each one of the DACs, we have a balance and filtering, amplification, and then we went through a circular two-way device, and then a harmonic filter on the transmit side to go out to the antennas. And likewise, the receive side is a path is basically same circular is driven down here to this switch that opens the receiver when they transmit it to protect the LNA. We have an LNA, and then we're going into an AND. And you repeat this 4 times. You've got 1, 2, 3, 4. So that's 4 transceivers, 4 receivers, 4 transmitters. And they all could be operating at the same frequency. You center the information bandwidth, or you could offset them as well. So really, you have a full capability in doing so. So you could use them all transmitting the same frequencies, where you have transmit diversity and receive diversity in this case to maximize signal. So now this was the detail of this. You can go back to my video and watch the details of this. But so all we need to go and make up a 5G mmWave transceiver out of this is basically get rid of the high power section in here, keep this section, the LNA. We're also going to eliminate this. This was the path where you take the PA, you can route the PA to the receive path to do like linearization and power control and other compensation for or to check your transmitter spectrum, just to validate the system, the transmit path. Okay, so all we need is an up converter section and an amplifier case. Okay, and so just so that we would so if you look at this, so what I did is basically took out, recycled the first section of the sub 6 gigahertz in here. So we've got the transmit section in here, got the receive section in here. And what I added a dual up converter and down, an up converter and a down converter. Up converter here, down converter here. And we have a synthesizer that generates the LO, okay? And then I moved the transmit receive switch here and utilize a front end LNA and a PA for mmWave frequencies. Okay, and then after that, of course, you have to drive the array. And in this case, of course, as I will show a little later, I'm going to need to split 16 ways because I'm driving 16 transmitters and 16 transmit receive TR antennas. So, and that's what I'm doing here is I split 16 ways. This is a passive distribution to the antennas. Okay. And then I have the beamformer. Right now, I populated only 2 sections of it, emulating the receive. In the receive, one is configured to the receive and one configured to the transmit path, which is right here, okay? And so basically, they have the switch in here. The switch is what controls either receive or transmit. And in this case, right now it's receiving. So receiving, meaning right now I have a signal right here, mimicking a user equipment terminal at -70 dBm out of the antenna that comes into the beamformer, which is made of this variable gain and phase shifter, digital phase shifter in here. And of course, this switch in here is what decides to route the signal between the transmit and receive for all the 4 paths. This is a beamformer chip that has dual polarization for TRs in it, 4 transceivers in it. Okay, so what I'm doing right now is I only have one cell out of the 4. The other 3 are basically terminated with 50 ohms. So this here, this section in here alone is basically the beamformer chip, which I will show you in a minute. And that's an off-shelf component. Basically, it comes in with digital interface to program the weights into the phase shifter and to the amplifier. And then it gives you capabilities of routing the signals, you know, for the different paths. So let's get back to the presentation. So, okay. So what we're doing in here, okay, is that what we will be doing. So we took one of these sub-6 gigahertz transceivers, and I made this. Oh, actually, no, we're still at the sub-6 gig. Okay. So what this is, let me go back to the other slide. Whoa, this thing went crazy. Okay. So we were talking about this here, okay? This is the sub-6 gig that I covered last time. So I'm still reviewing the sub-6 gigahertz system that I did last time. So we took this. This is 4R dual pole basically system. And so to make, you can double that, you can use another set of this, and you can actually get more of that. So you got 8 Rs. So all you need to do is just start stacking these like you see here. And this is usually what happens in a cell site. You have a few of these to cover the entire omnidirection. And this was the last time. What we did is basically, here's the transceiver design. All the components were picked off the shelf. And by the way, the last time when I simulated this, we are assuming that we are operating in an ideal situation where we did account, we had a margin for basically the loss between the stages, interconnecting stages to all of these devices, okay, and the copper. So you need to, somebody I think emailed me and wrote me that you need more than this. Yes, true. This is only a top level calculator, and this would have to be done on schematic based, and then BCB layout, and then simulated with ADS, and that's the next set of videos that we're going to do. So we look at this, I look at this, and now you need to realize this in actual chips. These chips have a lot of associated passives, and there's a lot of copper that traces connecting them. So really, what you see when we looked at the transmit receive, this is the passive distribution network for the 4. When we looked at this here, where we looked at the performance of the chain, the budget link into this chain, we really didn't account for all of that stuff. That stuff is still yet to be done. This design, usually we do this design at the top level. We go down into the ADS, we implement all the circuits and discrete components and put models for these ICs. And then we end up modifying again, coming back to this here, to this system level, and basically modifying all these components to include these losses. So this is a lot of iterations on this. This is a lot of work has to be done. Anyway, so you can get back to my other video and see all the stuff, how it's done. So now, so what we're going to do, we're going to take this here. We're going to remove the circulator in here and the high power section. Okay, we're going to remove the transmit receive, the termination receiver terminated front end termination switch that is here. We're going to remove that and recycle this section here to use it as an intermediate frequency for the mmWave, because we want to have these ICs, the front end digital front end, generate the IFs, the 5G modulated signals, somewhere between 3 to 6 gigahertz. And then we're going to take that in conjunction with a frequency synthesizer and an up converter, down converter, and take the signal up to the FR2 allocations and reverse it also for the receive. We have to do the same thing, except we have to down convert. So, okay, so let's look at that next. So we're gonna start here. So the first thing we're gonna do is let's start with here's a top level, sort of like rough specifications or features, the main features of this system that we're gonna design. So it's going to have 64 elements, and it's going to have 4x4 MIMO, okay? And it's going to have, again, plus minus 45-degree oriented dipoles, or cross dipoles that we call them, at 28 gigahertz. That's the intention, center frequency. Now, even though I'm saying it's center frequency 28 gig, but now remember, your DAC and your ADD has a huge bandwidth, like 500 megahertz bandwidth, so you can move anywhere in that. You don't have to remove, you don't have to synthesize your LO to move the frequency up or down between from this frequency, from this operating frequency. You could fix that, use a fixed LO, but then move your baseband so that when it comes out of the DAC, it plays it somewhere, anywhere you want, offset it. Now the element gain, I'm going to assume it's a 3 dB each one of these antenna elements. So there's 64 of them. So that means the theoretical antenna, the panel gain is going to be about 21 dBs. Okay. So having this number now, I'm going to also say, let's use a beamformer chip that gives 13 dBm of power into each element. Now that chip, of course, provides the signal for both the vertical, horizontal, plus or minus 45-degree polarization, you might want to call them. So having this number with the panel gain, and of course, assuming right now we're assuming that losses will be taken care of later. We're going to account for that somehow in the amplification. So we're going to theoretically, that means is that we are going to have 52 dBm EIRP. Okay, so that's the 52 dBm EIRP. Let's take out 2 dB as a budget for losses, feed losses. So we're going to have 50 dBm EIRP. Okay, so that's basically the intention for the design example. So let's look at the receive side. So if you have a plus 50 dBm, okay, EIRP on a small cell at 28 gigahertz, okay, somewhere in there, with a PA 13 dBm and a beamformer chip that has a 20 dB of gain, usually that's typically what you get from the beamformer chips that I'm going to show next. Now you got analog devices, you got Renaissance, you got Nokia, you got who else? Curva doesn't have one, but there's a whole number of startups in the US and Europe that, and even Japan and Asia that are producing, manufacturing nowadays beamformer chips for mmWave 5G market, because it's a huge market. So a lot of people are trying to get into it and make money. So typically that's what you get the TX gain of the beamformer chip. So assuming also go back to the from our previous design session in the presentation for the sub 6G at 3.6, we're going to assume that the DAC full scale is about 4 dBm, okay, CW. So allow 12 dB for the peak to average ratio of the 5G signal. That means the DAC level, we're going to drive out of it with minus 13 dBm. Now, why this important is because with this level here, with that, I can size my transmitter because I need minus 13 out of the DAC at somewhere, say, 3.6 gigahertz. I need to take this and up convert it to get to plus 13 dBm, okay? And that would be 26 dB of gain. Of course, you need that's the total gain between the antenna feed point and the DAC. Of course, that's really overall gain excluding all the losses. And when actuality, when we when we start implementing this, you have a lot of filters, you got passive mixers, you have so forth. So you're more likely to end up with about 50 dB or even 60 dB of gain, okay? Now, let's do the receive side. So you got EIRP of 50 dBm, okay, and 64 elements with 21 dB of gain, dBi, sorry, that should be dBi. Now, usually, if you look at the Rappaport model for millimeter wave signals in urban, suburban, so forth, at typical 10-meter height, small base stations, usually get somewhere between minus 60 dB, somewhere at minus 60 dBm up to like 500 meters at 28 gigahertz. Now, the signal assumed is a bandwidth is 400 megahertz, 64 QAM, and therefore you need 22 dB of signal to noise ratio. And you've got your ADD, of course, it's got about, it's 12-bit. So you've got the one I'm using here, that ADI 90, 85, 91. It's a few slides away from here, we covered it. So that has about 50 dB of dB full scale of signal to noise ratio, meaning you really have to take the received signal, which is low, minus 60 dBm, all the way somewhere between backed off level from the ADD level that's talking about that. What I'm trying to do is size the receive chain from the antenna to the ADD, basically. And so the sensitivity of the receiver, thermal noise wise, in 400 megahertz is about minus 58 dBm, assuming that the noise figure is assumed typically, which is 6 dB is for the beamformer chip in the front end, plus 2 dB of losses somewhere in there. So that you're most likely going to end up with a noise figure of about 8 dB. Now, of course, this is unlike the receiver that we did for the sub-6 gigahertz, the previous presentation, and you can check that video. The noise figure there was less than 2 dBs, okay? And that's different because that uses different technology, uses gas fits, and where this one here uses CMOS and silicon germanium for beamformer chips. We don't have a front end, separate front end with low noise figure. We rely on the beamformer chip alone. And that is usually implemented. The technology doesn't allow you to really get down with noise figures below this much figure, because you have splitters and phase shifters and again variable gain attenuators. So you end up with this kind of number for the noise figure. Now, so let's assume that we want to drive the ADD at minus 10 dBm typically. That's a good level. That's about 12, 13 dB of back off from the full scale. So that means if you're trying to detect this signal in here, that means you need at least 50 dB of total gain in the receiver. So that's what we're going to design it to. Okay, so and here is the design. So we took the sub-6G front section in here, the back end section, and we chopped off the section with the high power section, and then inserted an up converter and a down converter. And all we did is we just added a switch to try to switch between the feed network that feeds the plus 45 degrees, and then another network that here. Sorry, this is between the transmit and receive on one polarization and another one orthogonally on the other polarization. And we're using 64 elements. So in this case here, we have 4 transmit, 4 receivers, okay? And that's it's a 4T4R dual pole system, okay? Where 2 of the transceivers, 2 transmitters at plus 45 degrees, 2 receivers, 2 transmitters at minus 45 degrees, and so forth. So now, so here is what we're going to do. So this is the sub-6G that we did last time. We did it at the free operating frequency was 3.5. So we're going to eliminate all this section and just recycle this section in here and use it as our IF stage of the millimeter wave transceiver. And so I took and it's almost becoming a standard. All these chip manufacturers that do the beamformer chips, like this one in here, where you see in here, we have 8 beamformers in here. 4 of them are for one polarization and 4 for the other polarization. And of course, every one of them is a transceiver. So you've got to switch between either transmit or receive. It's a time division duplexing system. So I grabbed this off from Renaissance app notes. And so this shows how you'd use 64 elements with their beamformer chips in here. And you have a 5G baseband IF baseband to IF section, which generates the vertical and horizontal, they call them in here, which they mean plus minus 45 degrees. And you have an up converter section, which is like this. You have a transmit path which just up converts it, the signal with an LO, and then another one with the same thing except it's down converter for the receive path. Okay, and the LO usually comes from a synthesizer, and these mixers are usually subharmonic mixers. And that's what I used in my design. In my design, I did not use this chip. This chip has so much gain that I didn't need to use this. So I ended up using my own discrete mixer from Analog Devices, Hittites. But it was a subharmonic driven mixer where the LO gets doubled inside and the signal, the harmonic that is emphasized from the LO is a second harmonic conversion, okay? So that's becoming like a standard, okay? So you can see that the antennas are dual polarized. There's 2 distribution networks. There's 2 passive, 16-way passive networks. You got split 2 ways here, 2 ways here, 2 ways here, 2 ways, 2 ways. So you got 16 way splitter divider and 16 in the transmit path it's divider, and the receive path it's summer, of course. So it's almost becoming, this is becoming a standard implementation, and so that I'm going to just follow that, except a little modification with the and you're going to add, I added filters as well, because this serial does not really show the filters, okay? And the passive components in here, just you need all these passive components. You either the divider network, like I showed last time, you could design it either with Wilkinson's using strip line technology with thin film embedded resistors, or you could design it as you could off the shelf thin film two-way, 4-way splitters. And that's what I did, okay? So what I did is I went in the literature and just found from the manufacturer, several manufacturers make filters for these devices, for this band, FR2 band, for millimeter 5G. Like this example in here, for instance, this is from the Director Lab. So these are all centered at 28 gigahertz somewhere, all the activities. So I took these, and you notice the one in the cane, this one here, the pink color, that's what I use basically in my design. So what I do is I set my LO somewhere in here, and then my signal will end up in here. So you end up rejecting the LO and rejecting the lower sideband. Likewise, on the receive side, you set your LO so it's out here, and then your signal. Now the passive, I need a 16-way divider and summer, and that's basically here, okay? And this was designed in the last session. I think we went through this. So basically what I did is I use a 4-way divider from Noel's lab, from Director Lab formerly. No, sorry, this is from Mini Circuits. I apologize. Both companies make the same device. So, but I believe this, I'll show you in a minute. This is from Mini Circuits, okay? So basically that's what's, we're gonna come in here after the up conversion, and then all these signals are gonna basically feed the beamformer chips, okay? And the beamformer chips in them, each one of them feeds 4 antennas, of course, and that's, you end up with the beamformer implementation. Okay, so let's just review what I need. First, I use this baseband section, or the back-end digital section, which is made of the 80, 90, 81 from Analog Devices. So got the JEDES 240B in here, which is a gigabit back-end SerDec. And then, so this system in here, it's running DACs at 12 gigasamples per second and ADDs at 4 gigasamples per second. And from last time, as you can see, we generated 3.5 gigahertz out of this, okay? So at this rate, okay? And likewise, I'm sorry, at the DACs. And we sampled the 3.5 gigahertz with 4 gigasamples per second, and we ended up last time showing that what you end up with basically when you do subsampling like that, you end up with an IF, digital IF at 500 megahertz, okay? And we showed you've got these sections in here. All these sections are basically responsible for all the digital rotation to baseband, the downsampling, the filtering, the interpolation, and decimation on both sides of the transmit and receive. This is the chip that I'm going to use right now. So it's this is from Renaissance. It's the 288. And basically, as you can see in here, it's got a memory for the weights, store the weights. It's got a serial peripheral interface to communicate to all the with the memory and then load all these beamformers with the weights, okay? The shaded ones are for the one polarization, where the other ones are for another polarization. So as you can see in here, this can drive 4 antennas. So I could use this and this to drive one, this and this to drive one, this and this to drive one, this and this to drive one. And they're orthogonally. And you've got 2 feeds, of course, for the horizontal and vertical, like it's shown in here. Now, the receive mode and the receive path has got about 22 dB of gain. And the transmit path's got about 25 dB. So I use these here in the model that I built here. This model, that chip was modeled using this here. This is a 4 beamformers, 4 paths of beamformers. Okay, you've got one. Here's one. I didn't populate. I terminated in 50 ohm. Here's one. Here's this one. That's 4. Okay, and here's another 4. Okay, so this is just showing, and what I'm doing right now is I'm putting a signal in here, this signal at minus 70 dBm at 2700, 500 megahertz. That's a 5G antenna picked up signal. I'm going to show how you can receive the signal, how this actually comes in here and goes all the way to the down converter and to the ADD section in here. Likewise, on the transmit section, I have a transmit signal, okay, and right now I've got it at minus 130 dBm is because I've got the system here configured as a receive in this switch here. You can see the switch here. I've got it switched to the receive, okay, and so what I do is I kill the signal way down so it doesn't interfere with this. And the reason I did this so that I don't have to simulate this twice for transmit and receive. What I do is I just toggle, as I will show you in a minute. When I run this, I go in here, I make this minus 13 dBm, so 130, and then end up with the signal coming out on this side here, where this signal in here, I put it at minus 700 dBm. And that's like basically my way of implementing transmit receive switch. So let's finish. So these parameters, I store them in the model, okay? My LO signal is generated from this LO. This is a synthesizer chip from the TI or ADI LMX 2594, or who owned linear devices? I don't remember, but it's this chip here, okay? I think it's TI. Oh, no, it's ADI. We'll see in a minute anyway. So basically, it's got an internal BCO. All you need to do is just design the loop filter in here. They give you an app that could optimize the response and give you these the loop filter values. So what I'm going to do, I'm going to synthesize an LO that is at half of the frequency. So all I need to do is go up to 14 gigahertz. I don't need to synthesize. It can be just fixed LO. And so I put in 14 gigahertz, and 14 gigahertz inside the mixer gets doubled up. I've got a subharmonic mixer at X2, which basically synthesizes the up conversion and down conversion at twice the LO. So I feed it half of the LO, and that's why I use this. Another reason I use this chip is because it's got something called the sysref. It can generate sysref. And it's beyond the scope of this presentation to go on sysref, but what it is, you can generate also a signal that goes out to the codec, to the digital to analog and analog to digital, to sort of like synthesize for coherently routing, passing your data through the serial interfaces throughout. So this goes all the way, the sysref signal drives the digital to analog and analog digital converters, and also it gets routed to the FPGA as well, because you need a sync signal with all of these. This is a whole area where you have to design it so that you can actually, these samples of gigasamples per second, it can passes time mark them correctly and coherently get all your data in there. The VCO at 12.5 and 13.3 is listed here. It's acceptable, so check that. You could take this into your model for the Pathwave model, the SystemVue. So here's my entire basically hardware pieces. So, and I put this figure in here, which I borrowed from Renaissance for the moment. So we have the digital backend, we have some kind of interface to the up converter, down converter, which is hearted at the mixer, which is second harmonic harmonically pumped LO. We've got the synthesizer in here that synthesizes the LO. Okay, we've got some kind of circuit interface between the up converter. Of course, this here is where your sub 6 gigahertz IF transceiver implementation, which we just covered in the last video, and I just covered a minute ago, showed you, which I will show you in a minute also in the model. And so we've got the passive distribution. In this case, we've got 64 elements. Each each 4 elements is fed by one beamformer chip. So you need 64 divided by 4, that's 16 RF signals in there. So we're going to use a 1/16 passive divider on the transmit side. On the receive side, we use it as a summer that basically to feed the beamformer chip. Okay. Okay, and this is basically the top level diagram. So we've got the transceiver section in here that is running at 3.5 gigahertz. We've got the up converter and down converter section in here, which runs using a 24 gigahertz LO to either transmit or receive at 2750. Okay, and then we've got the transmit receive switch in here. We've got another filter in here, one of these off-the-shelf filters, okay, just to make sure that my signal is clean and reject all the spurious and harmonics. And then I've got a passive network of 1/16 using 4-way splitter off-the-shelf thin film power divider. And then I have my beamformer implemented as this. Right now, it's not popular. What I designed, left these open because these dividers have high isolation, so I don't need to even worry about terminating these with 50 ohm. You could terminate them 50 ohm if you want to, but I didn't. So I just implemented this 2 branches emulating a transmit and receive path. So this is the receive path. So which I come in here, there's 16 of them that come in all the way here, 16 that comes in here, gets summed in here, filtered in here, and then gets routed into this receive path in here, gets down converted, and all the way until the ADD. Likewise, on the other side, we got a DAC that plays the waveform at 3.5, it's converted to 27500 in here, go through a transmit switch, and then gets split to 16 ways, because you have to provide the signal to 16 beamformer chips, okay? So the filters, again, I'm using, this is the 3.5 gigahertz filter, which I'm using. And I believe this is from Johansson with this part number. There are other filters as well available from mini circuits and various Asian sources as well, Chinese, Taiwanese, and Koreans. So this is very much, there's a lot of people that manufacture, tons of these manufacturers try to compete to get into this, to get a niche, to get an entry into this, grab a piece of this pie of 5G hardware developments. The 28 gigahertz filter that I used is basically this filter here, which is an LTCC filter, and it's BFHK-2802. That's a mini circuit LTC filter. As you can see in here, it's a pretty nice filter, okay? And this filter, I use it throughout the beamformer distribution networks. Wherever I suspect there's interferences, or I need to clean the signal, or there's an LO leakage that is not acceptable, or a lower sideband or an upper sideband that is not acceptable, I throw one of these in, okay? So I ran this system, which is basically this here. So we're going to run it for both transmit and receive, and I will show you in a minute. So, and run this. So this is on the transmit side. So I start out with minus 13 dBm at the LO in here. The red is the transmit signal from the DAC. You can see I went all the way up to 13 dBm, 13.5 dBm signal at the beamformer chip, okay? This is at the antenna feed. This is including the beamformer gain on the transmit side. The bandwidth, the spectrum of the transmitter, you can see here the IF spectrum nicely and done, okay? And so you can see that we can drive from all these IFs, you can go up to, and you end up with 13 plus minus 2 fractions of a dB. Okay, this is really the conversion gain. What this shows you basically, except it's not showing gain in dBs, it's showing the output power in dBms. This is the DAC frequencies. This is not the RF frequencies. And here is the DAC output level. You can go all the way up, and it compresses somewhere around minus 9 dBm. Okay, so we're only backed off by a few dBs. Now, this is my current design. Now, you could come in and say, well, this is not acceptable. I need to back up more, in which case you're going to end up somewhere around, say, to 8 dBms or to 10 dBms. It's up to you. But this is what my current system is set up. So, so because of the beamformer chip has a limitation on the output power level. If you need to go beyond that, you really need an external front-end suction, which comes in as a PA on one leg and an LNA on another leg and 2 transmit receive switches. Okay, and that, of course, makes it more expensive. That would be a lot of EIRPs, but we're not targeting that. We're targeting 50 dBm EIRP, where 21 dB is coming from the antennas, and the rest is 13 dBm from the beamformer, which is just sufficient. Okay. Now, so let's receive side. You could look at the receive side. So we're going to look at this path here. In a minute, I will turn to the live modeling to show you how that is done. So the same wise, we start out with minus 70 dBm at each antenna input. And for the red one in here is basically the desired signal. From the antenna feed point into the beamformer all the way to the ADD, we can see that minus 70 dBm produces 13 dBm. So with a gain about 57 dB gain, RX gain in the front end. Pretty good, okay? So the overall noise figure in this case is 7 dBs, okay? Which is also acceptable. That's really nice. The 1 dB compression point is minus 21 dBm, and that's also excellent because there's no way that you can pick up a signal at this level unless you're inside the lab and testing the system where your transmitter is right across the table from you, okay? The frequency selectivity of this, you can see here, we got 27.2 to 28.2, very nice. So 1 gigahertz bandwidth. The compression, like I said in here, is really nice and neat. So okay, so let's turn to the modeling. So this is what I did. So you can start out right now. It's set up. So I have minus 70 dBm in here. So I'm going to configure this switch to go into here, and this beamformer chip in here, go in here. Okay, I statically put this at maximum gain, and this one at 0 degrees. Okay, and then we're going to figure this switch. This is all of this model here is not hard. This is the beamformer chip. I'm just mimicking the Renaissance beamformer chip. Okay, so configure all these switches. Okay, now this is the signal comes in here. This is the passive 16-way passive network. That's this. That's basically this network in here. If you look at the panel, that's basically the distribution network. Well, let me look at the bigger figure here. Okay, that's the distribution network that is drawn with these lines in here, as you can see. This is on the back side of the board. You've got the beamformer chips and the passive four-way splitters that I'm using in this case. Okay, that's what you see in here. That's what these are. Each one of these. This is basically this is the EP4KA plus. That's a mini circuit millimeter four-way. I believe this is a gas fit, probably a four-way splitter. Okay, and then I come in here. This here is configured to route. This is a transmit receive switch to route into the down converter section in here. The down converter section in here, of course, you've got your LO is running at 24 gigahertz. Okay, and your signal comes in here. Okay, and so basically, if I look at this signal, this is basically the performance. So you got the whole chain in here, and the signal starts out on top here at minus 70 dBm and ends up at the 80D input with minus 13 dBm. Okay, and these are basically the rest of the slides that I showed you. Okay, so right now in the transmit section, I don't have something in here, so it's all not done correctly. So what I'm going to do is, because I killed the signal on the transmit, so I'm going to go in right now and configure so that I go and transmit. So first thing, I'm going to put minus 13 dBm in here, so which I'm putting instead of minus 130 dBm, which is almost like basically you're muting the RF on the transmit section. I'm going to come into this switch that is here and switch over to the transmit by putting this into state 1. So now we're in the transmit path. And the transmit path, what I did is I configured this here to be my transmitter. Okay, I didn't use this one here. As you can see, this one is not switched in the transmit mode. So I'm going to do is I'm going to run this again so that we can get let's see, this is the signal here. So this is the transmit budget link. So I'm going to run this, and hopefully in a minute it will come up with the analysis. Still running. Should have saved a copy with this, but just to show you another thing also, while we're waiting for it to finish. The mixer that I'm using for this is basically this mixer, which is the HMC 338. Okay, so it's done. So let's look at it. Okay, here we go. Here's the data. Okay, so basically, as you can see here, we started with right now the RF level is TCP, desired channel power, which is in red, is minus 13 dBm out of the DAC. And what we end up with at this point here, and that point is basically the output of the beamformer transmit PA, or the beamformer. There's a transmit receive switch in there between receive and transmit. That's basically the output of the beamformer chip, which is 13.5 dBm. And the overall gain is 26 dB, like I started way back when we analyzed this and said that's really what we wanted. Okay, the noise figure is 13 dB now, and the noise figure is because we've got a whole bunch of passive components between the up converter and the DAC. Now, if you don't like that, you could start out, you put a buffer on your DAC with low noise figure, so you can actually reduce that if you don't like that. The 1 dB compression point is minus 11 dBm, okay, which is appropriate. Okay, ladies and gentlemen, so this really basically now, just to remind you that I do have an HFSS training 3-day session that I hold frequently. So if you have your company have few engineers that could come on site and deliver this to you, or you could fly over and come to this hotel and here where I hold this. And basically what I cover in there really is these videos in here. See, these videos in here are all microwave RF designs using HFSS. So you could, and that's basically what I cover in there. The other training that I have is on the Pathwave, both the SystemVue and the ADS. For SystemVue, basically what I do is I will cover all these videos in here. There's like 6 videos of various transceivers for SATCOM and cellular and GPS and so forth. Okay, so you could reach out to me on my phone number in here using these telephone apps, Android apps, or Apple apps, or you could email me on this email. I appreciate it to do that. If you have any opportunities where I can help you, please let me know. Until next video. So, ladies and gentlemen, so this is really going to be my last video probably on the SystemVue usage for modeling, for designing system level designs. So what I'm going to do next is jump over to the Pathwave ADS and HFSS again, ANSYS, to try to actually take one of these designs and actually take it all the way to implementation, where you can actually implement down to the board level and produce a board and actually get more into the real world issues that you will face when you're designing these hardware components. Until then, I appreciate it. Thank you very much. I appreciate seeing you. I hope you're learning, you're enjoying. If there's something that I missed or made a mistake, please communicate to me so I can learn from you. And I'm sure a lot of you out there have much more knowledge and experience than I do. I welcome you all. Thank you very much. Have a great day or night, wherever you are in the world. Thank you.